Hello and welcome to my YouTube channel. Today we are going to talk about a very interesting property of semiconductor devices, and apart from that, the behavior of electrons and how the mass of electrons and holes differ in semiconductor devices. Today's topic is effective mass model. Let's start the video. So first of all, let us try to understand what is effective mass model. The previous videos we have discussed about the chronic penny model, and we know that chronic penny model explains the value of momentum and energy values for which there is a quantum state or where the electrons are allowed to be. Okay, so chronic penny model talks about basically the momentum and energy of electrons, and it also talks about where these electrons can be situated. You cannot have the electrons roaming around the whole lattice. So now the question is how the chronic penny model can be used to further go in deeper mode and understand the behavior of electrons with respect to their momentum and energy. So if you recall, we had this chronic penny model where we have in x-axis the wave number represented by K, and in the y-axis we have the energy which is represented by E. If we take the help of classical mechanics, then we know that energy is given by mv square upon 2, which is the kinetic energy. And if we substitute the momentum in this equation, then the equation will be p square upon 2m, where p or small p is our momentum and m is the mass of electron. So here, let us talk about the energy bands. Energy band EC. So here we have the conduction band, okay, and in the bottom we have the valence band. Okay, now with the help of this chronic penny model, what else we can find? So remember, chronic penny model was actually developed by the help of Schrodinger's equation. If you go further back to my lectures, you can see how the Schrodinger equation helped the chronic penny model to evolve. So we can say Schrodinger's equation resulted in chronic penny model, and for every value of K, so every value of K, if you go to the axis of K, which is the x-axis, so for every value of K, there exist two values of energy. For example, if I take this point, okay, then you can see there are two values for energy. Now this is very interesting topic and might be a bit confusing for many people. So please carefully see this video. Okay, so now here it says for every value of K, we can have two different values of E, not a single value, two different values of E. And we found that in the Schrodinger's equation, m is given by h hat square k square upon 2e, where k is the wave number and E is the energy of electron or the fermions, or we can say the particles which follow the Schrodinger's equation. So for every value of K, you can see there exist two values of E. Okay. So with this, we can continue and go a bit deeper to understand what it means basically. So let us talk about the effective mass of electrons and holes. So let us start again with the same equation. E is equal to mv square by 2. Substituting the value of momentum, we get p square upon 2m, which is nothing but equal to h square k k square upon 2m. Remember, this is not the Planck's constant directly h, it is the Planck's constant divided by 2 pi. And if you see here, this equation is nothing but having a function which is more or less parabolic in nature. So if we draw the chronic penny model, we can see, yes, we have a behavior in the E axis which is more or less like the parabolic nature. Okay, so this function is nothing but the energy function. Okay, let us go a bit deeper. So m is h square k square upon 2e, which is coming from the Schrodinger's equation. Taking the first derivative of energy E with respect to k will be giving us this 2 will come here. Okay, h square k upon 2m. So this 2 in the numerator and the 2 in the denominator will cancel each other, and we will end up with h square k upon 2m. Let us give a name, third equation. Further, if we take the derivative of the energy with respect to k, or we can say the second derivative of energy with respect to k, so it will give us d square e upon dk square. Further, k will be k is having power of 1, therefore it will be gone. So h square upon m is the second derivative of energy with respect to k. Now, if we just move the m to the left side and bring the d square e upon dk square to the right, then we will end up with this equation where m, mass of electron or the charge carriers or particles, is equal to h hat square divided by d square e upon dk square. So this is our final equation, and here we can see a very interesting behavior. Let us explore that. So this equation is also having some parabolic behavior, or we can say something like a parabolic function. And if we see here, if we remember, when we provide energy to the electrons which are present in the valence band, they move to the conduction band, okay, leaving behind holes. So if we provide external energy, then these electrons will move to the conduction band, and in the valence band they will leave behind the holes or absence of electrons. So if we represent all the electrons have been moved to the conduction band, then that means lots and lots of holes will be left behind in the valence band. And if we check the behavior of mass, then in that case we can identify the mass here in the top, okay, is positive in nature, whereas the mass of particles in the bottom or in the valence band is negative in nature. So this is how we can find, or we can say, there are actually two different types of masses. One is the mass which is positive if you go above the axis or zero axis, and you have the mass which is negative if we move below the axis. Let us have more defined behavior. So remember, the curvatures of these parabola, okay, the curvatures of this parabola can be used to calculate the effective mass of holes and electrons. What do you mean by curvature of parabola? So parabola can be something like this, or it can have a behavior something like this, or which may be further flat. So all these three are representing parabolic nature or parabolic function, but the curvature of these parabola are different. So remember, curvatures of this parabola can be used to calculate the effective mass of holes and electrons. Remember, we are not calling it mass of holes and electron. Instead, we are calling it effective mass. So, therefore, we will represent it with m to the power star k is equal to h square or h hat square divided by second derivative of energy with respect to k. So, m star is nothing but the effective mass of electron. And for silicon, this effective mass is 1.08, and for holes the effective mass is 0.57. Okay, now let us go a bit deeper and understand what this effective mass of holes and electrons means. So from the previous slides we can conclude, or we can say that the energy curve of chronic penny model follows the square nature or parabolic nature, and hence it is similar to the parabolic nature. Second point to remember is that the electron's momentum is fixed. Okay, if the electron's momentum is fixed, then the corresponding energy is also fixed. So that means if the momentum is changing, the energy may also change. From the chronic penny model, it is evident that for every value of k, which is in the x-axis, remember k was in the x-axis and E was in the y-axis. So for every value of k, the mass of electron may occupy two energy levels. One, it may be either on the top or it may be below the zero axis. Substituting two different values of k will result in two different values of mass of electron. So depending on the position of electron, whether it is in the valence band or in the conduction band, okay, the value of mass or effective mass may differ. Last point, an electron's effective mass depends on where these electrons are situated in the energy curve. Okay, so energy curve is something like this. So if the electron is situated like this, then of course the energy of electron which is at the bottom is less as compared to the energy of electron which are on top of the energy well. So depending on the position of the electrons, the effective mass may differ. Okay. Now, from this we can say if the energy function is highly curved, that means something like this. If it is highly curved, then the effective mass is almost negligible. This means that particle responds strongly to the change in momentum, behaving like a lighter particle. So, effective mass is also related to the curvature of the energy function, whether the curvature is like this or it is more flat in nature. Depending on the curvature also, the energy function or effective mass may change. Okay, so precisely effective mass can be thought of as an inversely proportional to the curvature of energy function. So effective mass can be thought of inversely proportional to the curvature of energy function. So let us just briefly talk about some of the values related to the effective mass of electrons and holes. In case of germanium, the effective mass of electron is 0.55 to the actual mass of electron, whereas effective mass of hole is 0.37 to the mass of hole. Similarly, for silicon, the effective mass of electron is 1.08. Effective mass of hole is 0.56. For gallium arsenide, the effective mass of electron is 0.067 and for hole it is 0.45. Remember, the if you go and check the energy well of germanium, silicon or gallium arsenide, you will find that these wells have different curvatures, and depending on that, if these electrons are situated in these wells, then they have different value of energy associated to them, and correspondingly the mass is also different. So here m star n is nothing but the electron's effective mass, m star p is the hole's effective mass, me is the electron's mass in rest. So if the electron is in rest, then in that case me is the mass of the electron in resting position, mh is the mass of hole in resting position. Please go through this presentation. If you have any doubts or suggestion, please share your doubts and suggestion in the comment section. If you have not subscribed the channel, then I would request you to please subscribe the channel and share this video with your friends. Thank you and have a nice day.